Right. So this leads us to ask the question. So what can we do about some of the technologies we can develop that allows us to fly at high speeds in the transonic range, but without taking too much penalty? So people have come up with various ways. I don't think this is an exhaustive list, but these are some of the things we can do as aerospace engineers to achieve that. So number one is to make the wing thinner. So instead of using a thick section like the NACA 0015, for example, that's quite a thick section. What you guys will find if you research very carefully, that modern transport aircraft flying in the transonic regime, they usually have thinner sections compared to other aircraft, for example, low speed ones. Right, so that's the first one. And it's really to do with the same thing, right? Delaying the drag increase and delaying the formation of shock waves, or making the shock waves weaker if possible. And that reduces your drag. Number two is using supercritical wings, and we'll discuss this in a few minutes. Okay. Again, they try to do things, create weaker shock waves, so it gives you the lift you need, but also gives you less drag. Okay. Number three is using wing sweep. And I'm sure for all of you flying to your holidays over the summer, you will see that virtually all modern aircraft, transport aircraft, have swept wings. And it's actually to do with what we've been discussing. And I'll show you why in a minute, why we sweep the wings. And number four is reducing the aspect ratio. So that's another solution. Again, is trying to do the same thing. So let me just discuss some of these technologies. So here I'm showing you a graph of the drag coefficient on the y-axis as a function of the stream Mach number, which is the flight speed, basically. But I'm showing you here. Now, first of all, what you guys see is the general shape I've shown you for the drag is definitely there. They all have the general trend, but at different levels. And this is given for different thicknesses of your airfoils. Remember, when we say thickness of the airfoil, we're referring to the maximum thickness, because obviously the thickness is distributed, is not constant. So T over C, that's the maximum thickness of your airfoil. Anyway, so the one that at the top here is thickness to chord ratio of 12%. So that's quite a thick airfoil. And then we have 10%, 8%, and 6%, right? And clearly what you guys can see, first of all, the level of the drag as we make the wing thinner has reduced, which is good news. But let me see what happens in terms of delaying the onset of the drag rise, because that's, remember I told you, that's really one of the key things. And hopefully you guys can see that. So if we look at the first one, which is 12% thick, you guys can see, okay, as usual, fairly constant drag coefficient. After that, it starts to increase slightly. So that's probably where the critical Mach number is. And then suddenly, at around, well, just below 0.8, you got the sudden drag rise for that particular thickness. Now, if you compare that with thickness of 10%, clearly, guys, you can see that this drag rise is actually delayed to over around 0.86, right? Which is good news. Now, if you do the 8%, is even delayed to 0.88, maybe, something like that, before you get the drag rise. And then finally, with the 6%, delayed just over 0.9. So clearly, you guys can see, as you make your wing thinner, it allows you to fly faster and delay the drag rise. And of course, flying faster, we all want to fly faster, of course. This is very important for passengers and aircraft operators. It's always the promise of, going from one destination to destination in less time. Everyone is attracted by that, obviously. And of course, for operators, if you do it faster, it means you can have more flights, so more revenue. Anyways, but clearly, I hope you guys can agree that the thinner the airfoil section, the higher the speed we can achieve, and we delay the drag rise problem. Is everyone clear? Good. So let's look at wing sweep. Why wing sweep is good for trying to fly faster? Well, one way of looking at it is to look at basically what is the Mach number the wing is seeing for a non-swept wing and for a swept wing. So on the left-hand side, we have a straight wing, so it's not swept. There's no sweep in this wing. And therefore, whatever the wing will see whatever Mach number the aircraft is flying at. Okay. Now, if we sweep the wing by creating sweep angle lambda, capital lambda. Is this lambda? I'm not sure. I always get. Is it capital lambda? Any Greeks here? That's capital lambda, isn't it? I think it's capital lambda. Or is it capital alpha? I don't know. Who knows? Yeah. I think it's lambda. Anyway, so you introduce this sweep, okay, usually either at the leading edge or quarter chord, it doesn't matter. So there is an angle there, typically around 15, 20, 25, something like that. So in this case, what the wing actually sees, it doesn't see M infinity. It actually sees M infinity cosine of that angle, which is obviously a reduced Mach number, which is good news because remember, you don't want the flow, well, what's happening really for a given Mach number, so the actual flow that the wing sees is less than M infinity, okay? Which means in reality, then it will speed up less and therefore the formation of shock waves is delayed, if you guys think about it. So this means we can increase the critical Mach number M infinity to higher Mach numbers before the drag rise occurs, okay, which is good news. And therefore, effectively, the aircraft can fly faster with a swept wing because we're delaying that drag rise. Exactly what it is. So this is why this is just a picture of a modern, transport aircraft, and you guys can see the wings are highly swept, and it's exactly for that reason. So next time you guys sitting on this aircraft, you must know that somewhere on that wing, there is possibly a shock wave somewhere, okay? And hopefully it's probably not a very strong shock wave. Obviously, there's a lot of drag, but there could be a shock wave on that wing. But the reason we're having those swept wings is to allow us to fly faster without a huge penalty in drag. If you had straight wings, it's really, you can't go faster before the drag rise catches up with you and you're basically dead. You can't really, your engines will have to work really hard. Right, one way people look at sweeping the wing is actually in terms of the effective chord of the wing. So it turns out that if you sweep the wing, the effective chord will increase, okay, so that the effective thickness also reduces. So we kind of come back to a thin airfoil. Okay, by sweeping the wing, the effective chord goes bigger. So for a given thickness, the thickness will go down, and we kind of go back to this case. So this is kind of another way of looking at the effect of sweep. Right. So if we look at this is just two graphs. Obviously, I won't be mean to ask you to draw those in the exam. But this is just an illustration showing you the difference between swept wings and swept wings in terms of the lift and drag curves. So here is the drag curve, the top one. The first one is unswept, and you guys can see that. Can anyone tell me from this graph what is roughly the drag divergence Mach number? Roughly. Roughly? Huh? No, just over 0.8? Yeah? Yeah, that's true. So you guys can see that the sudden increase in drag is just beyond 0.8. So probably the drag divergence Mach number is around here. Right, what if we sweep the wing? Well, you guys can see that. First of all, what do we have here? We have an extreme case of 45. Usually we don't actually have a sweep of 45, it's quite high, but it's probably maybe some military aircraft or something. But anyway, just to illustrate the point that you guys can see the rise, the drag rise is delayed to higher Mach numbers. So this aircraft here can only fly up to around 0.8 and then it gets the drag rise. But this one here clearly can fly at higher Mach numbers before the drag rise occurs, and that's because of the sweeping the wing. Another way of looking at it in terms of lift is to say the following. So what we have here is the pressure coefficient plot, okay, for the same aircraft, one with 0 sweep, flying at free stream Mach numbers 77. The other one is with sweep angle of 20 degrees, okay, and flying also at, well, with the sweep angle. This is what the effect of the sweep will happen, will mean. So to achieve the same CP plot, this CP plot is achieved at this Mach number, so it's a lower Mach number, free stream Mach number. But this one here, because I told you as you sweep the wing effectively sees a lower Mach number. So for the same Mach number that the wing sees of 0.77, the flying Mach number actually is actually 0.82. So the aircraft with sweep is actually flying faster to achieve the same local flow Mach number on the wing of 0.77, and that's using 20 degrees sweep. So you guys can see here, this aircraft can only fly, well, it's flying 0.77 to achieve this lift, but here it allows it to fly at 0.82, which is obviously what you want. So that's sweeping. So I just thought I'll give you some things to think about. Maybe, obviously in engineering, there is no perfect solution. There's always pros and cons. So I'm just listing here 2 disadvantages of sweeping the wing and how we might deal with that. Obviously, if you guys have any better solutions, please share it with us. We're all colleagues. So the first problem that could happen with sweeping the wing is tip stalling due to more flow heading to the tip, and also the boundary layer becoming thicker and it may separate. And of course, thicker boundary layer also is not good because you get more drag, more viscous drag. So how do you reduce that, or how we can mitigate for that is you can twist the wing, okay, or maybe add a fence, okay, which stops these effects from happening. Number 2, in the grand scheme of things, having swept wing will not allow you to take off and land at the very low speeds that you require during takeoff and landing. It turns out that the landing and takeoff speeds are increased, which is not good news, okay? Aircrafts land and take off at low speeds. Swept wings increase those takeoff and landing speeds. So you have to do something about it. So what you can do is you can use much better lift device, high lift devices. We're going to talk about high lift devices in a minute, actually. So you have to employ high lift devices so that you can reduce the takeoff and landing speeds, okay? Or just reduce the sweep of the wing, just to reduce that effect. Right, the last thing I will discuss before we have 5 minutes break or something is supercritical wings. Our friends at Airbus, have you guys worked on supercritical wings? Yes? No? Have they told you about supercritical wings? Have they told you about their supercritical wings? Not yet, okay. You are their employees, they haven't, okay. Yeah, all right. So supercritical wings, this is a kind of a fancy word you hear around, but it tries to do the same thing as thin wings and swept wings. So again, we're trying to achieve the lift and drag that allows us to fly very fast without the penalty of drag rise. And interestingly, the concept of supercritical wing is attributed to who? Does anyone know, historically? Very famous guy? British guy? Come on, guys, you should know him. Very good, yeah. French guy knowing a British guy. Come on, guys, what's going on? You're making me look silly now. Okay. Right, okay, yeah. Richard Wickham, yeah. So Richard Wickham was working with NASA in the 1970s. He was playing around with kind of trying to change shapes of certain airfoil. I think it was a NACA series. And he actually introduces this particular shape called the supercritical. So what are the characteristics of supercritical? How do you recognize an airfoil or a wing to be supercritical? Well, typically, first of all, now if you look at a conventional airfoil, you guys can see there is quite a lot of curvature on the upper surface. On the other hand, supercritical actually has more or less flat surface on the flat upper surface compared to the conventional one. That's the first thing. Number two is to do with the leading edge. So the leading edge radius for supercritical is larger compared to the leading edge radius of a conventional. I know these two graphs do not really demonstrate that, but this is what it's meant to be. What else? Number three is, if you guys can see this, this cumbered section here towards the trailing edge on the lower surface, okay? So once you see that, you know this is most likely to be a supercritical airfoil. So you may not appreciate why those characteristics, but really, honestly, they try to do exactly what I've been saying, which is basically reduce the effects of shock, okay, and try to delay the drag increase, the sudden drag divergence that we see on normal wings. So these combined design changes apparently lead to that. So first of all, if we look at the fact that we have a larger radius for the supercritical wing, this allows the flow to go faster compared to a conventional one. So going faster on the upper surface is good because it gives increased suction, less pressure, and therefore more lift. So and now what happens is that once the flow speeds up, because the surface is flat or relatively flat, that speed up effect is maintained over a longer period, more or less the same speed. Okay, so it doesn't. So this is a kind of a curved section. So it will, if the flow speeds up here, it will speed up even more, and that will end up in a shock wave just over a smaller distance on the upper surface. But because the supercritical wing has a flatter surface on the upper surface, it allows a much larger area of the supersonic flow to develop, and it's only much later that you get the shock wave. And the good news is that that shock wave is actually much weaker than the shock wave you would get on a conventional airfoil, which means the wave drag here is reduced. Okay, you're maintaining supersonic flow here, which is good because that will give you more lift. But at the same time, you're doing that with a weaker shock, which is less drag, which is obviously we don't get with the conventional airfoil. And okay, what else? Now, this region here also helps in giving you more lift. Okay, so the combination of really all design features is basically more lift, less drag. So they kind of, these supercritical airfoils, they sound almost like ideal, but this is really what they do. And it all starts in the 1970s. Nowadays, I can tell you that a lot of aircraft that fly in high subsonic to transonic Mach numbers, they most likely have supercritical because everyone realizes you can save a lot of fuel by having a supercritical wing. And I'm sure a lot of Airbus aircraft are already probably with supercritical sections, but obviously they don't tell anyone, neither do the Boeings and the other aircraft manufacturers. But surely when you see all these benefits that allows you to fly faster, getting your lift and less drag, clearly everyone wants to do that. So it's definitely, I'm pretty sure that a lot of aircraft these days, they use supercritical airfoils. Now, why is this a good news? Less drag means less fuel. So the operators, they don't have to spend money on fuel, means all of us can travel faster on our holidays with cheaper tickets, isn't it? It's good news. This is kind of the profound effect on our life that started from 1970 to present day. It's quite an important thing to remember. Okay, and I think, for example, here, a very famous aircraft that actually was tested on the supercritical idea is the F8. And if you guys have a hawk eye, you can read here is actually supercritical wing. Probably very difficult to see. But anyway, this is one of the very famous aircraft that was tested with a supercritical wing. And actually, another famous aircraft is the Boeing 777. It has a supercritical wing as well for all the things I've been talking about. Here, just finally to finish, I'm showing you here just kind of a CP distribution. So remember I told you that the lower surface where it's cambered, it kind of tries to give you more lift as well, and this is actually observed here. So this higher region here for the supercritical means you're getting more lift due to the camber, due to this region here, okay? So this is shown on the CP curve. Remember guys, the CP curve, the area within the CP curve tells me how much lift. The higher, the better, okay? Remember that. And you can learn really from, remember I told you is the flat surface of the upper surface. This is actually also reflected in the pressure. So if you plot the pressure coefficient for a supercritical wing on the upper surface, it's kind of more or less flat, reflecting that particular. It's kind of, if you look at it, it's actually more or less follows the shape of the airfoil, the supercritical airfoil itself. But this is one way of recognizing it. What else I can say? Yeah, this huge drop here in the pressure, that indicates a stronger shock wave compared to smaller drop in pressure with supercritical airfoil. So this is another way of recognizing a weaker shock compared to a very strong shock on normal airfoil. So this is really all I want to say about a kind of flying subsonic to transonic region to demonstrate some of the important issues that we need to think about and kind of the profound effects that they have, and hopefully you can see why people have thought about these solutions, or some of these solutions, to actually deal with the problem itself. And I'm pretty sure there's still a lot of research nowadays trying to improve these things further as we want to fly faster and faster, of course. We still want to do that. Any questions? We take a break.